Okay, Doppler shift time. This is the little demonstration I did in class where I had that ball, that styrofoam or that foam ball with the little alarm in it that I was swinging over my head to demonstrate the Doppler shift. And so this question on page 73 of your lecture tutorial gives you a little introduction to the Doppler effect. And what we see is that in the situation A, this is a situation where your source, the star, and your observer are not moving with relation to each other. Essentially, we're pretending that this is your stationary situation. And you get a wave that looks like this. Now in situations B, C, and D, we notice that the star is moving away from the observer in situation B. In situation C, the star is coming toward the observer. And in situation D, it's kind of moving neither toward nor away, but it is in motion. It just has what's called no radial velocity. Here, you have a radial velocity away from the observer. Here you have a radial velocity toward the observer. Here it's neither toward nor away, it's just kind of to the side. So in question 1a, they ask, in which situation will the observer receive light that is shifted to shorter wavelengths? Well, notice, if this is the one that we're comparing to, which of these has a shorter wavelength? Certainly not this one. This one looks the same. This is the only one that has a shorter wavelength. Notice this wave is a little more crunched together. So that's situation C. Is that a red shift or is it a blue shift? When your source is moving toward your observer and you have this crunching, or this decrease in the wavelength, that is what we call a blue shift. It's not necessarily, like I said, it wouldn't be that the light would turn blue all of a sudden, but you would have, again, a shift of all the wavelengths to shorter wavelengths. So if maybe you're looking at just the gamma rays. Well, gamma rays don't really have a color to them, but whatever the value is for this gamma ray, that same wave produced by the star, if the star is moving toward you, would be shifted a little bit to the lower wavelength or the higher frequency. That's what we call a blue shift. And so what direction is the star moving relative to the observer? Obviously, it's moving toward the observer. In question 2, they say, in which situation will the observer receive light that is shifted to longer wavelengths? So again, we're using this to compare. We notice, okay, that one's a longer wavelength, right? This was smaller. This was no change. So this is a longer wavelength wave now. And what do we call that? We call that a red shift. Again, not necessarily because the light will look red. Again, we could be looking at something that doesn't really have a color. We could be looking at gamma rays or radio waves, but if the wavelength you expect now it seems to be a longer wavelength, that tells you, okay, the light has been shifted to a longer wavelength, and we call that a red shift. In which direction is the star moving? Obviously, it's moving away from the observer. All right, flipping the page. It says in number 3, page 74, in which of the situations will the observer receive light that is not Doppler shifted? Well, situation D, because there, and of course in A, because there's no motion away or toward. In situation A, the thing wasn't moving. In situation D, it was moving, but it wasn't moving radially away or toward the observer. Now question 4 says we've got 3 stars in our Milky Way galaxy. And star A is slightly closer to us than the other 2. Star B is a red star that is farthest away. Star C is a yellow star that is halfway between stars A and B. But notice that our solar system is moving toward all 3 of them. That's the key. So it says which of these will give off light that appears to be blue shifted? Well, they all will, won't they? Because we're moving toward all of them. So the relative motion of the source and the observer in all those cases would be getting closer together. And therefore we would see a blue shift for all of those. This question B says, which would show a red shift? Well, none, because in order to have a red shift, you have to be moving away from each other. And in situation C, question C, which will give a no shift? Again, none of them would, because we have relative motion here. It's not like they're not getting close. It's not like they're essentially at rest to each other. Question 5 says, here we have a couple of students discussing the topic, and student 1 says, since Betelgeuse is a red star, remember Betelgeuse is the star in Orion, it must be going away from us, and since Rigel is a blue star, it must be coming toward us. Again, Rigel is a star in Orion, and Betelgeuse does indeed look reddish, Orion does indeed look bluish. Student 2 says, it's not because of the motion of the star, it's because of the temperature. It says the color of the star does not tell you that it is moving. You have to look at the shift in wavelength of the lines and the absorption spectrum to determine whether it's moving toward or away from you. And so yes, student 2 is correct. The color of the star tells you the surface temperature of the star. It doesn't tell you the movement. You look for the dark lines or the absorption lines and see whether they are where you would expect them in the laboratory or if they have been shifted a little bit. So the actual color of the star, just by looking at it with the naked eye, tells you about the temperature, not necessarily the motion of the star. All right, moving on. I'm going to try to knock this out in this one video here. On page 75, we see 3 absorption spectra. And notice that the layout is the same. We've got 1 line here, 3 lines here. 1 line here, 3 lines here. 1 line here, 3 lines here. We have to pick out, of these 3, which one is a star that is moving toward you. Because we've got one that is moving toward you, one that is moving away from you, and one that is essentially at rest. And so C has to be the one that is moving toward us. Because remember, we would be expecting a blue shift from motion toward us. So we'd be looking for lines that have been shifted in, toward the left. The only one that is possible here would be C. And therefore B would be the one that's moving away from us. And therefore A would be the one that's at rest. So this is the one we would compare to. Notice that in C, these lines have all shifted to the left. That's a blue shift. In B, comparing to A, all the lines have moved to the right. That's a red shift. And the more the shift, the faster the motion. And that's what we get to on the next page. Question 8 asks, which of the 4 spectra would be from a star that's moving the fastest? Well, again, we'd have to refer to the diagram on the previous page, but E is the one that's would be the correct answer there. It's going away. We see a red shift there. G, which star is moving the slowest? Well, it's going to be G. It does show a blue shift, but it's a very small shift, so it is moving toward you. It's a blue shift. Question 10, instead of giving you the dark line spectrum, they just tell you the wavelength of a particular absorption line. So we expect to find an absorption line at a wavelength of 656 nanometers. And that's not necessarily true when we look at all these different stars, H, I, J, K, L. The wavelength is different for these different stars. And so we have to decide, okay, if we're expecting to see an absorption line at 656, and we don't see it there, what does that tell us about the relative motion of these stars? Well, stars that would be blue shifted would be ones that would have the absorption line at a smaller wavelength or higher frequency. And that would be both L and H, because notice with L and H, those values, 649, 647, those are less than 656. So again, those have shifted that. A line that we expect at 656 is now at a lower wavelength. In B, which ones are redshifted? Well, I and K. Why? Because I and K values are higher than 656. So that shows that we have shifted that absorption line to higher wavelengths. And then which one has been shifted by greatest amount? This is question C. That would be L, because that's a big shift. Instead of being at 656, we're all the way down at 647. So it's moved to a shorter wavelength. In D, which one is moving, which star is moving the fastest? Is it moving toward or away? Well, again, L is moving toward. It's the one that shows the biggest shift. It's 9 nanometers away from the expected value. All right, last page. We've got 5 objects here, A, B, C, D, E, and 4 planets and a space probe. And this thing, that's our source. The space probe is the source of our signal here. And question A says, which will receive a radio signal that is redshifted? We'll notice that in our diagram, the space probe is moving toward B and E. It's moving away from A, and C and D is actually moving kind of just, it's neither toward nor away. And so A would receive a redshifted signal because the probe is moving away from it. In question B, it says which planets will receive a radio signal that is shifted to shorter wavelengths, or a blue shift? Well, that's going to be both B and E are going to receive a blue shifted signal. In C, the question says, will they all receive radio signals that are Doppler shifted? No. C and D would get the original, whatever that source frequency is, whatever that wavelength is that this thing is putting out, that's what C and D are going to receive, because there's no radial motion there. It's neither moving toward nor away, C and D. And then finally in E, I'm sorry, question D, how will the size of the Doppler shift detected at planets A and B compare? Where A and B, this probe is going as quickly toward B as it is going as quickly away from A. So they're both going to receive the same shift, same amount of shift. The difference being that A is going to see that shift as a red shift, and B is going to see that shift as a blue shift. And question E says, how will the size of the Doppler shift in the radio signals detected at planets B and E compare? Well, again, this probe is coming toward both B and E at the same speed. They're both going to receive a blue shift, and it's going to be an equal amount of blue shift. And that's it. Hope you enjoyed.